Hey pre-calculus friends, here we are in section 1.6. We're going to be modeling real world data with linear functions. A lot of this vocabulary you will recognize from us talking about it in previous lessons this chapter. So we've got one, let me do this a little bit out of order. So if we started off with, let's say this term, scatterplot. A scatterplot is just when you put data that you might get. Let's say you are doing, comparing something like shoe size to height, okay? So if you were doing something like that, you might collect a bunch of data. This person is this height, and this person has this shoe size and this height, this shoe size and this height. And so you might see something that looks like this, okay? Not strictly, maybe even something like that. You can, the larger shoe size, maybe your height is a little bit taller, you might get something like that. That's a scatter plot. That's what a scatter plot would be. And so a lot of what we're going to talk about is really based on this idea of what a scatter plot is. So if we take this scatter plot and we consider the fact that there seems to be a linear relationship, like a positive linear relationship, then this next word, line of best fit or best fit line, would be you taking a line literally and trying to see if you could figure out how to make it fit the best. Like, do you have to kind of change the slope a little bit? Where would the y-intercept be? And you would try to find the line that fits best given the data that you have. And that line of best fit, if you were to find the equation of it, that could become for you a prediction equation. And so what a prediction equation is an equation that you would use to discuss like other points that are not represented in the data. So let's say, for instance, my data about the shoes only went up to a size 13. And then we were like, oh, there's this dude with size 15 feet. I wonder what the data would say his height would be, right? So given the prediction equation, we can use the prediction equation to kind of extrapolate and say, well, perhaps his height would be somewhere here if the relationship between shoe size and height works. Are you guys with me? So the prediction equation, you would actually get a formal equation, a y equals mx plus b type of equation perhaps, and you would use that based on the line of best fit or based on the data that you have to predict for information that you have no data for. So the goodness of fit, and I'm glad you asked, what is the goodness of fit? The fact of the matter is, when we deal with the line of best fit, some lines are not going to be as good as others. When I taught this before, like years and years ago, when calculators were not as ubiquitous and easy to get a hold of, I would actually teach this with a dry spaghetti, like a piece of dry spaghetti, and we'd have the kids try to figure out what is the best place to place that line in the data. Okay, dry spaghetti gone. But the fact is, if I gave 20 kids dry spaghetti to fit the same data, we'd probably get 20 different equations, 20 different lines, because everybody sees things differently. So there has to be some way to judge how good your line is, how good that approximation is. And so that's what we're referring to here with the goodness of fit. So the way the goodness of fit is actually judged is by something called a correlation coefficient, and that's going to be R. And we're going to talk a little bit more about the correlation coefficient as it relates to the Pearson product moment correlation. So that's going to be referred to as R, and in a sense for us, we're going to be talking about R from the Pearson product moment correlation in the same way. So R tells me how good the line is in terms of representing the data that I've given it. And there's a really nice video on YouTube that goes into detail. It's about 14 minutes long. Goes into detail about the correlation coefficient R. And R is going to only be from -1 to +1. And so the further negative it is, that's the further confirmation that you have a negative slope and that is a good representation of the data. And the further the positive is, that's going to be representing the fact that your line is really good and it's a positive slope. And everything in between will be kind of how well it refers to a linear equation. And I'll show you a little bit about that here. So here's the video that I saw that I thought was pretty good, and I'm not going to
Writing's
play
not
it.
that easy.
I'm going to try not to play the commercials for you, first of all.
This tutorial, another in my series on correlation and regression.
Okay, so I know that was inelegant, but what I wanted to show you is that the video exists. Take note of it if you want to get more information. I stole this from the screen, or I copied it from the screen, and I thought it was a good way to explain what the Pearson product moment correlation value is, or our correlation coefficient. So it's a value that is R, and it's going to be between -1 and 1. -1 means you have a strong, solid, linear negative slope, and that's the relationship that you're representing. The +1 means that it's a strong positive slope relationship in terms of being a linear relationship. And here, between those values, let me write on this a little bit. Between those values, like this could be like, let's say, a -0.8 R value. Let's see if I can write on it again. -0.8 R value, something like that. Let's do it down here. -0.8 R value would be this guy up here. This might be a +7.5 R value up here. And this one, where there's no relationship, doesn't seem like it's linear in either direction, it would be a 0 R value, or a 0 correlation coefficient. So it kind of gives us an idea of how good the line would be, or how good the data is really leaning into a linear equation. And as I said before, there is definitely a video there that if you want to get some more information how it's calculated. It's not beyond you, but it's beyond the scope of our discussion for today. All right, so finally, the last thing we have is linear regression, and I will highlight this here. Linear regression is really using the calculator to you're giving the calculator data, and it's going to give you what the linear equation is for it. And we'll be doing that within the confines of this discussion, and we'll also do it using Desmos. So here in example 1, this is coming from the beginning of the chapter. We're going to take a look at some data and figure out what to do with it. So the cost of attending college is steadily increasing. However, it can be a good investment, since on average, the higher your level of education, the greater your earning potential. The chart shows the average tuition and fees for a full-time resident student at a public 4-year college. Estimate the average college cost in the academic year beginning in 2006 if tuition and fees continue at this rate. Well, clearly in this case, we've been given some data, and that data is going to set the tone for how we're going to create our equation. And 2006, that's something that's not contained within our data. We need to use a predictive equation. To simplify things, I'm going to call this year 0, and this year 1 and 2, 3, and so on. This way, when I put the information into my calculator, my graphing calculator, I'm not dealing with super huge X values. And so I can think of the 0 as years from this college year, this academic year, years from 1990, 1991. And so I can do that, and now I can use that to tell me what 2006 would be. Can you think about what 2006 would be? Well, we know that the 1999 to 2000 would be 9 according to our numbering system, and therefore 2000 would be 10. So we can see that we are looking to predict for 16, because that would be the year 2006, 2007. Okay, so that would be the academic year. So that's what we're looking for. And so I'm going to go ahead and get Desmos in on this. And you all may remember from before, when you call up Desmos or anything like that, you can just type Desmos in, push enter, click on, greatest graphing calculator in the world, or whatever it says, and then you can get started. So you get to this screen, you want to go ahead and put in a table, and I'm not going to bore you with me putting this table together. I think you guys know how to do it. You just click and plug it in. So we're going to put our table together. And so I've placed all my information in here, and you got to double check, because sometimes you do silly things. And so I'm just actually looking through, and I'm like, oh, I've got 311 and not 3,111. So little things like that, you just want to make sure you've done a good job of inputting your information. And now the calculator will do the rest of the work for us in terms of graphing. So what I want to do here is I want to change the look of my graph. I'm going to go up to the little wrench here, and I'm going to make this a little bit larger, or at least make this fit my data a little bit better. My X values do go to 10, like 10 is a good place for me to end, but I definitely want to probably just go back to like -1 so I can really focus on the positive portion of the x-axis. And my y-axis does not need to go all the way down here to negative values. In fact, I can, I don't know, start at maybe, I can start at 0, but let me make sure I get all the way up to a positive 5,000, let's say. And so that should show me my dots. Beautiful. So there are my points. And now I need to consider making a line of best fit, or a line of best fit that works for our eyes, right? So the technique that we have that's going to be hard for me to demonstrate here would be to actually just draw a line as best I can through that I think is really good, hence my spaghetti. Remember we were talking about that earlier. So draw a line through the data and see if what 2 points like it hits closest to, and I'm going to use those 2 points as an approximation. I'm not going to draw a line because I can't right now, so I'm just going to choose these 2 points because it looks like that's pretty good. If I were to draw a line connecting those 2 points, I kind of have a good sense of the data. Maybe these 2 points would be better. I don't know. See how hard this is sometimes? All right, maybe these 2 points. We're going to use these 2 points. I'm settling on it. So now what I'm going to do is choose this as my line of best fit, and then I'm going to go and find the equation of this line using these 2 points. So given 2 points, the 2 points that we picked out, I need to find the equation of a line. There's a bunch of ways we can do it. I think obviously we know that we need to find the slope first. So let's calculate the slope and let's find the equation in, let's say, slope-intercept form. So our slope ended up being 147, and our y-intercept, we can try to calculate that, but we should recognize that our y-intercept would be the value when x is 0. And so we made x 0 here in the beginning, so that would be our y-intercept. So that leads us to our equation relatively quickly. Y is equal to 147x plus 2,159. And so now this leads us to a really easy place where we can get the answer to our question, what will be going on in 2006 in terms of the cost of college. And so what we would do is simply plug in that 16 in for our x value. And it will be done like this, adding 2,159 rather. I don't know where I'm getting that 56 from, 59. And so when we calculate that, we end up with 4,511 as our answer to the question. In this last example, we'll be looking at using the calculator more to deal with our data. So the table contains the fat grams and calories in various fast food chicken sandwiches. And so we're going to first start off by using the graphing calculator to do something called a line of regression. And this is different in every calculator you're using. If when I see you in person, we can talk about the type of calculator you're using. If you're not using Desmos, let's do that. But I'm going to quickly put this information into Desmos. So I've put in the data and I've adjusted my screen so we can have a good visual of what's going on. The next thing I'm going to do is I'm going to find that line of best fit, that line of regression. And this, for Desmos, what you're going to do is type in the letter Y sub 1. So you're going to use the next line, and you're going to put in a Y and then the number 1, and it becomes Y sub 1. And what it's addressing is it's saying, hey, look at these elements in this column, and you want it to equal to, but you're not going to put equal. You're going to put the, I forget what this is called, tilde. You're going to put the tilde sign. It's usually like close to the number 1 on your keyboard. And then you're going to put M X sub 1. So what I'm doing is trying to get this into what is it called? Slope intercept form, X sub 1 plus B. And so it's going to, this is so cool, the calculator itself is going to give us an R value, right? And it's going to give us the slope, and it's going to give us the y-intercept, just like that. So we do actually have an equation, and so we can get our equation by cobbling this information together and substituting it in. So I've copied the slope, I've copied the y-intercept, and here is my equation that's going to be used. And they said use this equation to predict the number of calories in a chicken sandwich that has 20 grams of fat. Notice there's already one value for 20 grams of fat, though our prediction equation might come out different. Let's check it out. So according to our prediction equation, we get 460.3 as the value predicted given the other data that we have. And so you notice, yeah, it doesn't exactly fit with this particular data item. And I'm wondering why. I'm wondering if you have an idea why. If you think back to our graph, let me see if I can get there really quick. If you think back to our graph, why do you think this prediction equation doesn't fit our data exactly? Listen, take care. I'll talk to you soon.